Hi everyone, welcome to my channel and welcome to this video. In this video, I'm going to discuss about one of the most popular ways to interact with the Linux kernel, to extend Linux kernel, and perhaps the only way to interact with devices that's connected to your system, that is to your Linux machine, right? So if I ask you, how can you interact with your kernel or take help from your or take services from your kernel, right? Or use the features provided by your kernel. So perhaps the first answer that you'll give me is like use system calls, right? So if you want to read from a file, again, the primary interface that's provided by the kernel are files, right? I mean, if you want to write something to the if you want to write something to your disk, of course it's in form of files. You need to open and write to them. If you want to read write something to your network, to send something to another device via network, you need to open a socket file descriptor and read write from it, right? And to all those things, you need to do something called you need to use something known as a system call, the open system call, read system call, write system call, delete system call, I mean the unlink system call, and so on and so forth, right? Now if we go a level below that, and if I ask you, how can you extend your kernel, right? If you want to write something yourself that runs, so all these things that we do in our system, it's mostly in the user space, right? You create a file, it's in the user space. You create any application that's running in your user space, like, and whenever you want to write to a file or you want to write to the network, you are basically calling the system call. The system call is then running basically in the kernel space, right? And that's when the kernel comes into picture. Your process goes to sleep, kernel takes over, it does the things on your behalf, on your process's behalf, and then the control returns to your process, right? So the code that's doing all these things for you, it's not really your code, right? I mean, by not your code, I mean it's not the code that you have written as part of your application. It's the code, or it's the services that the kernel already providing to you. It's a contract that you have with the kernel that, hey, if you need my help, call this system call and I'll come into picture and I'll help you out reading this file, writing to the network, reading from the network, and so on and so forth. Now let's say you want to write something which runs in the kernel space. In a way, you want to extend the kernel with some new functionality of your own, right? How can you do that? If I put it in the other way, let's say there's a device, any sort of device, your keyboard, for example, your keyboard or your mouse or your speaker, your external speaker, your all these things. So like how do you use them? Like you basically ask the kernel to interact with them and give you the desired input or provide them with the desired output. And how the kernel does this is basically using something called device drivers, right? Which works in the kernel space as a part of the kernel. Some of them come with your Linux kernel, some of them you can install, and that's how you use them. That's one form of code that works in the kernel space, doing things on your behalf, interacting with devices and helping you out. So in general, like these programs or these extendable programs that runs in the kernel space, created by some user, of course, some developer, and they run in the kernel space, allowing you to interact with devices and other providing you with other services. These are known as Linux kernel modules, or in short LKMs, as you might see in several places, referred to as their short form LKMs. And these modules are basically like the architecture or the infrastructure that Linux provides you. By virtue of that, Linux is a operating system, or it's a kernel which allows you to extend it with the help of externally loadable modules, right? And these are the Linux kernel modules. So you can write your own module and you can load it into the kernel without shutting it down or anything. You can just load your code, your code in form of kernel module into your Linux kernel, and you can get started with using them there and there on the fly, right? That's the advantage that Linux provides to all its users, to be able to extend the kernel. If tomorrow, if a new device comes up, and let's say you have created a device, let's say you have created a USB device for yourself, and which you want to use with the kernel, all you need to do is write a device driver for that kernel. So for example, it can be a serial device that you have come up with, and for which you want your kernel to interact with. So all these things you can extend your kernel with such device drivers to onboard such new devices. So kernel provides you with this immense power to extend it, to modify it on the fly by virtue of these things called Linux kernel modules. So in this video, we'll explore Linux kernel modules a bit more in detail, not too much detail, but in some detail. And what we'll try to do is we'll try to create a device, or rather a device driver. We'll try to create a device driver which acts like a pseudo counter, right? So basically it will be a device file, and which will be located inside under /dev. So all device files are located in /dev. Most of the, like, you can keep it anywhere, but the standard device files, the convention is to place them in /dev when once you are done with your development. So anyways, so we'll come up with a device driver module which will expose a device file, something like a device counter or something like that. Let's call it counter dev, right? Let's call it counter dev. So what the device file counter dev will do is, whenever you write a number to the device file, it will increase the counter, which will be initially initialized to 0. It will increment it by that much amount. So if you do a echo 10 pipe sudo t to that particular device file counter dev, it will increase the counter by 20. If you write 30, it will increase it by 30, and so on. And whenever you cat that file, that is whenever you try to read from that file, it will simply give you the current value of the counter. So let's say you first do a echo 60, then echo 60, then echo 100, and then if you do a cat, it will give you 220. 60 plus 60 plus 100, it will give you 220. And what we'll try to do is, we'll try to do a rotating counter, which is the moment it reaches 999, that is 999, it will rotate back to 0. That is, whenever it reaches 999, and if you add 1 to it, it will become 0, and from there it will again start counting. So that's how. So the counter will get reset to 0, and it will start counting from there again, from 0 again. So we'll create a pseudo counter. So that's what we are going to do. We'll make the kernel count for us. If any program wants to make use of this counter, all they have to do is open the file, write to it, and then read to it whenever they want to write something. And we will also take care that no two files can use it at the same place. So to maintain consistency, the counter itself doesn't get corrupt due to consistency issue. So we'll make sure that at any given point of time, only one program or only one process is able to open that file, or rather, even in the same process, only one. If that file is already opened, we cannot open another instance of the file, right? So we'll do that as well. So yeah, so that's what we are going to do. We are going to explore device drivers, and we are going to understand how kernel modules work, how we can load a kernel module, how we can design one, how we can play around with it, and how we can build it, and so on, right? So as always, without further delay, let's get started. Okay, so before we jump into designing our kernel module and using it and playing around with it, let's understand a few things first. So if I draw the stacks of our operating system in let's say layers, I mean a very, very abstract stack design of the operating system, not very detailed, then of course the first layer is the user space, right? User space. And all our applications, for example, this application right now where I'm drawing it, my paint, it's running in the user space, right? So this runs all user apps, right, which are designed by developers. And this has got all your various files, ELF files, binaries, and so on and so forth, right? And then there is this other layer, the layer beneath it. Let me just make this a bit broad. I mean, yeah, bigger than the above one. And this is the kernel space, right? This is the kernel space. And here, whatever program or whatever code that's running directly belongs to the kernel, right? And they run with full privileges, and they pretty much they are running on the ring 0 of the CPU. If we consider the ring architecture of the CPU, the modern processors, like, they have rings. So usually the user space runs in ring 3, which is not the privileged one, which has security restrictions and things like that. And the kernel space and the programs in the kernel space, they run in ring 0, which means all the programs or all the code running in the kernel space is pretty much running with full privilege. And here you have the various kernel features, and the bridge that connects these two is basically something known as the systemv ABI. Like, we have already discussed this in one of our past videos, how systemv ABI is used to invoke the system call. So basically, whenever a user space program needs the help of a system call, it uses the corresponding wrappers present in the libc. For example, the write wrapper for the write system call, the read wrapper for the read system call. Again, sometimes the libc ones, the libc write, read, they are themselves referred to as the syscalls, but in reality they are not the actual kernel system call subroutines. All they do is they take help of the system v ABI, which is like they put certain parameters in certain registers, then the system call number in the accumulator, and then they actually make the system call trap, that is the syscall trap, or earlier it used to be the XAT interrupt, to let the kernel know that, hey, like I want to execute this particular system call for which I'm the wrapper. I've already populated the parameters. Now you take over and you call the actual system call subroutine. So the kernel would come into picture. It would, as a response to the trap or the interrupt call, it will find out the parameters from the accumulator. It will get the syscall number, and then it will find the corresponding syscall wherever it is located, and then it will execute it. And then the kernel code will take over, and the kernel system call code will take over, and it will provide the desired service, right? So the system call ABI. So again, system calls work at the kernel space, and this is like the bridge which joins your. It's basically, it acts as an interface for the system calls, right? And now this system call could have been to open a legit disk file, to open a character device, or to open any network file descriptor like a socket file descriptor, or anything and everything. But that's the entry point to your kernel. And interestingly, this is where the device files, the device driver codes are also located. So as extendable and loadable modules, right? Or rather, I should say the kernel module code that runs in kernel module code, that too runs in this space. So all the kernel module code runs as part of the kernel. So that's a very important thing that we need to keep in mind while designing this kernel modules, that the kernel modules run as a part of the kernel and not separately. And the fun part is the entire kernel runs more or less like a single program. That would be too much of an abstraction, but on a high level, it runs as a single program, sharing the same memory space, unlike the user space, which is paginated. So anything here that runs on a paginated memory, which means one program cannot access the memory space of another program, right? That's why we have logical address and physical address in memory, right? So basically every process in user space pretty much thinks that the entire memory belongs to themselves, whereas in reality the other memory space that does not belong to that process is invisible to the process. However, in the kernel space, that's not the case. So the module that's running in as part of the kernel, basically the kernel runs in a single memory space, so it pretty much has access to the entire memory that's allocated to it. So this is something which is extremely critical, and we need to keep this in our mind. Why? Just imagine if a C program running in the user space, it tries to access a null pointer, right? It tries to access a memory which does not exist. So the first thing that will happen is the kernel will come into picture, and the program will receive a seg fault. The process will face a seg fault. It will receive a 6F from the kernel, and the program will be the default disposition of that signal 6F will kick in, which is basically the program termination. The process will be terminated, and a code dump will be taken by the kernel, and it will be saved on the disk. So that's what would happen if a process would try to access a invalid memory, because in this case kernel is there to protect our system, right? It would kill the process before it can do any harm. So now the question is, if in the user space it's kernel that takes care of things like this, handling these kind of exceptions and things like that, who takes care of such issues in the kernel space, right? So if your module code tries to do something funny like this, trying to access an element which doesn't exist or things like that, who takes care of that? The answer is no one, right? If your code breaks in the kernel, it's pretty much your kernel that breaks, and worst case what can happen is you would have to reboot your system to restart it in a good state. So that's the reason why we need to be extremely careful when we are writing kernel module code. The reason being, there is no one to save us if something goes wrong in the kernel. And this is something which we need to keep in mind, right? And this exactly is also a reason why it's always preferred not to do module development work in your current live system that you are using for everything. You can do it's fine if it's your local system, and if something goes wrong, you can always restart your machine. That's fine. It might be an inconvenience though while you are developing something. The other approaches that's suggested is that you can use something like a virtual machine, right? You can use a KVM virtual machine, or you can use a separate device altogether. In my case, what I have been doing is I've been using a separate Raspberry Pi Zero, right? It runs a flavor of the Linux operating system. So I'll be mostly using that to test out my kernel modules. I'll be developing it on my main machine, but to test it out, I'll simply SCP it into the Raspberry Pi Zero, compile it there, and then do a INS mod. So INS mod is how you load a module into the kernel, right? So yeah, I'll be using a Raspberry Pi Zero to test out my modules. Cool. Now that we know this basic stuff, let's try to write a very simple module to get started with, which does nothing but prints hello world in your D message, right? So D message is a very nice way how you can see outputs from your kernel module to do debugging stuff and things like that. So let's get started with that. Before we can start with our kernel module development, we need to install certain headers, basically the kernel headers. So that's pretty straightforward. And to do that, all we need to do is I've already installed them in my machine as well as on my target system, that's Raspberry Pi Zero. But all you can do is simply do a sudo apt update followed by sudo apt install linux headers hyphen uname hyphen r. That's it. And this will get you the kernel headers corresponding to your kernel. So now I have just created a simple folder, and I'll start with this module will be a very simple module, right? As I mentioned, it will mimic a pseudo counter device, or basically a pseudo counter. I'm calling it pseudo all the time because it's not an actual device, right? It's just a pseudo thing that I'm building. There is no physical device, right? It's just the device file that we'll be using, and the device file itself will maintain the counter. There is no actual external device or internal device that's counting anything for us. It's all in the module code, or rather the device driver code. So first I'll just create a simple, as I mentioned, I'll create a very simple hello world module, which will simply show hello world in the D message. And so for that, I'll call the module name as counter dev. So I'll start with certain headers. Okay, that's with all the header imports. And one thing you'd have straight away noticed is that although I said that I'll be outputting something to dmessage, I have not included anything like stdio.h, right? Which is like the standard input output header that we always use, stdio.h, right? Which is like one of these standard C library header files, and which is used in almost all terminal based program for writing something to the output to the terminal. The reason for that is the standard header files or the standard library is something which is implemented at the user level or the user space. So this entire libc from where the definitions of things like printf and all those things are located, the entire libc thing is a user space concept, not a kernel space concept, right? Like you cannot use your usual printf and all those kind of things which is available in the user space libraries but not in the kernel space library. So in the kernel space you can only use those built-in functions or libraries which are already present in your kernel space. For example, sprintf is available in the user space, right? You can use it in your user space applications, user space C programs. Interestingly, the kernel also provides an implementation of sprintf. So good thing for us, we can use sprintf in the kernel space in our module. So certain functions will have their corresponding implementation for the kernel space, and for the others which are not present, you will have to find alternatives or implement it yourself. Okay, so next what I'm going to do is I'm going to create a function that will be called the moment the module will be loaded into the system or loaded into the kernel. So let's do that. So this underscore init is nothing but a macro that gets expanded to attribute. It's a compiler directive. It actually expands to an attribute. It's a directive for the compiler, which tells the compiler to place these functions at certain places in the final binary that gets created, such that the system can free up the memory occupied by this function once their execution is finished. Usually you will see that there's init and there is another directive called the exit. These are used for functions that are called one time in the lifetime of the code, when the module is being loaded and when the module is being deregistered or it's being removed, right? So it simply tells the compiler that place it in such a space such that the memory occupied by that space can be raised by the system once the execution of the function has been completed. And here all I want to do is just do a basically do the equivalent of printf, right? I just want to print something to the message. For that I will use this function which is called pr underscore info. And fun part is there's not even a function, there's just a macro provided by the kernel for us to log stuff in the message. So whatever the kernel spits out using pr info, you can read it using the dmessage command, right? All I want to print is hello world from my module. That's it. That's all I want to print. And I would do a return 0. And the other thing that I'll do is I'll create another function which is called void underscore exit counter def exit another void, and I shall write something like time to leave. That's it. It's pretty simple. Now I need to tell the kernel when the module starts, that is just when the module is loaded into the kernel, I want to run this function, and when it is removed from the kernel, I want to execute this function. So how do I do that? And before that I made a typo here, and it should be Linux here as well. Actually I needed another header file. So how do I register these functions as the init and the exit functions? That's pretty easy as well. All I need to do is call these functions module init and module exit. I hope there is no typo. And finally I would like to give this module a license, and I shall give it GPL. So that's it. That's our 22 lines hello world kernel module, right? Now what we need to do is I missed another one now that I think of it. I hope I did not miss any other header files. Okay. So now the next thing that we need to do in order to actually be able to build this C file into the actual kernel module object, which has a extension called .ko, we need a build file. And the way we compile these kernel modules is a bit different, right? And let's see how we can how we do that. So I'll create a makefile, and the first thing is I would need this variable called obj-m, and all I need to do is add the object file here that gets created when it gets compiled. This is just a variable for the current directory. And there is nothing much to explicitly understand here. It's just the standard procedure how you compile or how you build a kernel module. It's just a standard makefile pattern for kernel modules. And finally I'll also make a recipe for cleanup, right? That's it. So that's our make file. Let's try to build our module now. So we have got two files, counterdev.c, which is our the C code for the module, and the make file. All I'll do is make. Okay, there seems to be some problems. Oh, that's my bad. Shouldn't have put return 0 here. And it got compiled. And it does generate a bunch of files, but out of all these files, the one that we need, which is our actual module, the kernel object file that will load into the kernel, is this one, counterdev.ko. Okay, so now we know that it actually compiles on the system. So now what we'll do is we'll transfer it to our Raspberry Pi Zero. I'll just split the screen too. Let me just enlarge this one as well. Okay, so let me first SSH into the machine. So it's 192.168.68.61. This is my Raspberry Pi Zero machine, right? And into which I have just now SSH'd. I'm inside the home, if I'm not wrong. Yeah. So for this video, I'll create a new directory called ytlkmpg. Inside that, I'll create a folder called hello world. Let's call it hello world. So this is where I'll be putting in the source code. So I'll be transferring both the things, both the C code and the makefile. Let me quickly do a pwd here. Okay, scp dot slash star. I'll be transferring everything to the pi 0. Actually, no, I don't want to transfer everything. I do not want to transfer the compiled or the build files. So I just want to transfer counterdev.c and the makefile. Yep, I've received both of them. And here too, I had previously installed the kernel header, so I won't be doing it again. And all I need to do is just do a make. Okay, so it's built, and we have got the counterdev.ko. Yeah, we have got the counterdev.ko here. Okay, so before proceeding, a little bit on the Raspberry Pi Zero for those who don't know about this device. It's offering by the usual Raspberry Pi Foundation, and it comes with 4 core. It's a tiny device. It comes with 4 core and 512 megabytes of memory. Yeah, and I believe I'm using a 64 gigs memory card for the OS. The OS it uses is, let's see what it uses. It uses Debian. I feel it's a Debian derivative, but I feel the name of the OS is Raspbian or something like that. I do not remember. All the instructions to set up the operating system and to flash it is available on their website. Let's do a uname -r. It uses the 6.12 kernel. What does my main system use? I don't remember. Okay, it uses 5.15. Cool. Now, what I'll do is I'll do a insmod, and I'll insert the counterdev.ko kernel object, and it's done. So just a quick thing for ease of reading. Let me just add a new line here. Let me quickly once again transfer the files. I'll just transfer one this time, that is counterdev.c. Okay, right. So I'll make it once again. So now I'll do insmod once again. And now let's check dmsh, and let's perhaps check the last line of the message, I'll do a tail -n1, and there we have it. There is of course a typo in hello that I have done, and it says hello world from my module. So yeah, the module got loaded into the kernel, and just after it loaded, the first thing it did is it executed this function, and it says hello world from my module. Now what I'm going to do is I'll be removing this module from the kernel, and for doing that, the command is again pretty simple. It's called rmmod, and what I'll do is I'll type in the name of the module, and let's check the message once again, and it says time to leave because this function got executed. So if I do 2 here, so you'll see first it did a hello world from my module, and second time it did a time to leave, right? As simple as that. But the fun thing is that this entire execution of the program is very different from the program that we write on a day-to-day basis, like a normal C program which we compile with GCC and then do a dot slash to print. It's entirely different from how that program or process works, because that program will be heavily relying on the user space libraries and all those things. Like it's running entirely in the user space. But on contrary to that, this program, this piece of tiny code, is actually being executed within the kernel, right? It's not outside the kernel, but it's being executed within the kernel as part of the kernel. So that's a very big difference. It's running in kernel space. It has got full access to the kernel memory, which a normal process or a program running in the user space does not have. It doesn't have that privilege, right? So that's a 22 line, a very simple hello world kernel model for you, which we just now loaded, executed, and then we removed it, right? Now let's start with writing actually a character device driver, which will actually create a device file here as an interface. So once we insert the next module that we are going to write, or basically we'll be updating this module, what will come up here is a new device file, something like a counter dev. We can decide on the name. Let's say that the name of the file will be counter dev, and there will be a device file here called counter dev to which we can write and read from, right? We can write a number to it, and we can do a cat on that to get back the value of the counter. So let's do that. Okay, so now let's start with our counter device implementation or counter device logic, which will actually help us count. Pretty simple, but it will show us the basics of character device. So once again, before jumping into that, the implementation, let's see a few things about device modules or device driver modules. So usually, as I mentioned at the start of the video, the device driver files or the device files are located in or under /dev. All these files correspond to some physical or virtual device connected to your machine, right? Yep, TTYs are also, terminals are also considered as separate devices. And so now let's see certain properties of this device file. So first thing, if we do a ls-l ls-l/dev, and if I do a head-n10, so if you see all these, against every device file there is this two numbers. For example, against this AutoFS or whatever, against this ButterFS control device file, there is something called 10, then another number called 234, right? So what is this 10 and what is this 234? So the first number in this series of two numbers is called the major device driver number. The first number is called the major device driver number, and second one is called the minor device driver number. So all device files have, or rather all device driver created files have two numbers, a major number and a minor number. So what are these major and minor numbers on these device files? So the major number indicates which driver is controlling this particular file, right? So this number 10 indicates which, to the kernel, it identifies which device driver has created this file, or rather which device driver is controlling this file, or rather which device driver is controlling the device associated with this file. So that's a identifier used by the kernel to know, right? So now what's the minor number? So one device driver can control multiple device files and hence multiple devices. So the minor number helps the device driver itself to distinguish between different devices it's controlling, right? So the major number acts as an identifier for the kernel to know which device driver is controlling a particular device or file, and the second minor number helps the device driver itself to distinguish between the different devices that it's controlling or it's meant for. And as I also mentioned earlier, devices are of two types, right? Character devices and block devices. So accordingly, there are two types of device drivers. One is character device driver and the other is block device drivers. So now, since there are two types of devices, block device and character devices, what is the difference between them? So the block devices, they allow you to buffer requests, which means they can decide which request to serve at what point in time. So they can order between requests because the requests are getting buffered. So this feature in particular is useful for disks, which can optimize requests on the basis of the order, depending in which sector the data is located, and so on. And for the character devices, they do not have this feature of request buffers. For them, whenever the request reaches the driver, it needs to be served. So there is no concept of buffering there. That's one difference. The other difference is block device drivers usually receive data in form of blocks or in terms of blocks, where the block size can be defined by the developer who is designing the device driver or the device. So the unit of data in case of block device drivers or block devices is blocks, which can be defined. The values of the blocks can be defined. But in case of characters, the unit is bytes, where it can be a few bytes to as many bytes as you want. So data is basically transferred in terms of bytes, however many bytes you want. So those are the major differences between a character device and a block device, and accordingly a character device driver and a block device driver. And from a device file itself, you can figure out if the corresponding device is a character device or a block device. So if you see, in case of a character device, it starts with C. So C stands for character device. And let's try to find a block device. Yeah. And if you see my disk device, SDA, that starts with B, and B stands for block device. So that's how you can differentiate between character devices and block devices. And also let's see one more thing. Okay, so for example, let's consider these device files. So now we know that what this essentially means is that all these device files and the corresponding devices are controlled by the same device driver, and these are the numbers which the device driver itself used to differentiate between these corresponding devices, right? So the major number identifies the device driver and the minor number identifies the device for the device driver, right? So that's a few basics of device drivers. Now there is one thing: the kernel provides us with APIs to kernel module APIs to register a device driver, and while registering the device driver, you need to provide the major number. Now there's a problem with that. Every device driver that's registered with Linux has only one unique major number. So it might happen the major number that you are coming up out of the blue can already be used. So how do you prevent this conflict? And there's also a provision by which, while registering the device driver, you can provide 0 for the major number, in which case the API will give you back the major number. But in that case, how would you create the device? So first you need to register, you need to somehow print, maybe you can use prinfo to log the device number and then create the actual device by hand. So it will be a two-step process. Or there is a location called /proc/devices. From there also you can pick up the major number and create this device by hand. So just like we have got mkdir for creating directories, for creating device files, you have got mknode, right? Using mknode, you can create device files, provide the major number and minor number. Major number you will get from the logs or from dmessage or from /proc/devices, and you can create the file. But again, like there's also a pretty cumbersome thing. It's not cumbersome, but it's two-step rather than registering the device in just one shot. It's now two-step, where you first register, then create the device file. To solve this problem, the kernel provides another API which is called device create, wherein you can actually use this API to create the device file itself from the device driver code itself, and it gets initialized. That is in the init function, and then in the exit function you can clean up the file as well. So that problem is also taken care of by the kernel and its APIs. So now let's see how we can use these APIs to create our device driver module. Okay, so now let's first start with registering our device driver and creating the device file as we discussed. And also, before doing that, I'll include some more header files which we need to create this driver. This fs.h is particularly of extreme importance because this is where this header file is what provides us with the underlying file structure, and also it provides us with the file operation structure. In a moment, we'll be discussing what are those and why we need those. Okay, so that's it with the includes. Now let's extend our init function so that it can take care of the device driver registration as well. So as and when required, I'll be declaring some variables. So first, let's declare the variable which will store the major number that will be returned to us. We'll also create a static variable for the class. We'll use this to create our device file. So I'll remove this. Actually, I'll log something like device driver registration initiated, something like this. And first, let's register it now. So the function I'll use is register chrdiff, and I'll pass 0 because I want the kernel to allocate me a major device number. Oh, I need a name for the device, right? Okay, so what name can I give? Device name, I shall call it something like, let's call it counter dev. And now comes one of the interesting parts. In the third parameter, we'll be passing a reference to something which is known as a file operation structure. Now, what is a file operation structure? So let me first define it. As I define, I shall explain what is a file operation structure, because without first declaring it, I cannot pass its address. So let's define that. Static struct file operations let counter dev fops. So it's a common convention to end it with fops, and what it will contain is, if the file is definition in fs.h, you will see that it contains a lot of fields. For now, the ones that we'll be needing is read, write, .open, .release. And from these names, you can pretty much understand that it has got something to do with the file operations, and that's the reason why this structure is known as file operations. So let's think about it in this way. From a user space, when you are writing to a device file or reading from a device file, there needs to be corresponding functions which allow you to do that. What I mean is that if you are reading something from a device file, a character device file, then there needs to be some function that's providing you with the data that you are reading, right? And if you just flip the coin, if you are writing something to a device file, then there needs to be a function which is actually reading that data that you are writing to the file. So here in this case, you just need to, when you are programming a device driver, you need to think from the perspective of the kernel or from the other side, right? So if you are outputting something into a device file, there has to be a function which takes that data as an input. And if you are getting some input from a file, that is, you're reading from a file, there needs to be a function which provides that data. So for that function, that it will become an output, right? So it just gets reversed in the device driver world. So basically here you need to define what are the corresponding handlers. So when you are reading from a device file, which is a handler that will take care of the read operations. If it's a write operation, then you need to specify a handler function that will take care of the write operation. Same for open, and release is what releases the device file, right? So for that, once again, what I'll do is, I have actually not defined the functions. What I'll simply do is I'll declare the functions, and the signature of these functions are pretty constant, are pretty standard. So it's not that we can do anything else with these functions. We need to comply with the signature that the kernel provides us. So let's start with device open. We have device release now. I'll soon explain what these parameters are for, but for now I'll just define them. Okay, so now I'll just simply point to these ones. This will be device read, device write, device open, and device release. And now we can come back to our registration function, because the registration function is to know which file operation structure you are associating with this file, so that the kernel knows from where it can call the handlers to handle the requested operation. And I'll pass it the address of counterdef FOPS. Now we'll do a quick check. If major is less than 0, which means it failed to assign it a number, basically it failed to register the device, so we will print an alert saying that registering char device file failed, with whatever error we get. Okay, and we'll return from the function. Otherwise, we will log the major number that we were assigned. Device driver has been assigned major number %d. And now we actually create the device file with the device name of our choice. And for that, we need to use a quick macro to determine which Linux version we are on, because the function signature is different for both for class create. We'll get to know in a moment. So otherwise it's called this module device name, and finally end if. So now that we have got our CLS variable initialized, basically our class initialized, now we can actually create the file. So for that, we will call device create. We'll pass CLS as the first parameter, then null, then mkdef. That's another macro. And finally device name. And that should create our device. So let's do a log device created on /dev %ls \n device name. That's it. That's our registration function. Basically an initialization function which will also register our device file and our device driver, character device driver. Okay, we need to extend our exit function as well to do some sort of cleanup, and that would also be pretty straightforward. forward. We need the major number here. And finally we shall unregister major comma device name. That's what it accepts. That's it. And so first we destroy the device, we call device destroy, then we do a class destroy, and finally we unregister the character device calling unregister chardev or chrdev. And finally let's keep it time to leave, or let's do a proper logging. Let's say device driver unregister. Cool. That's our initialization, and that's our init and exit functions extended to support the device driver that we are writing. Okay, so now that we have our registration and deregistration functions, or rather init and exit methods set up, now let's start with the file operation functions, right? So basically our file operation handlers. So first let's start with open. I'll start from here, just after the exit function. So as we know, before writing to or reading from any file, we need to first open it, right? That's for any file. And in case of kernel modules, we would have to provide the handler function for what happens when someone does a open syscall on that particular device file, right? And what we want to do in this case is, what we want is, since we are counting, since it's a counter, and since we want to keep it a very basic and simple counter, we do not want multiple processes to open this counter at the same time, or even we don't want the same process to open the this counter simultaneously, right, at the same time. So basically no two process can open this device file at the same time. At the same time, no, in the same process there cannot be two file descriptors, independent file descriptors present to the same file, so that the counter is consistent, like simultaneous writes are not happening to the file. So for that, we'll use something known as atomic compare and exchange, or rather atomic compare and exchange function in C. Basically, which it's provided to us by the kernel, and it's called, and basically what it does is cas, right? It does a compare and swap. So we'll have a compare and swap. So we'll have a variable called cdef not used, and so we'll basically have a function called already open, right? We'll have a function called already open, which will be of type atomic underscore t. As the name suggests, it will be treated as an atomic variable. And what we'll do is, it can have only two values. One is it's open, or it's not open, or rather it's not used, right? And if it's already being used, it cannot be set to open, right? It can be set to open only when it is not used. So that's where cas comes into picture. First we'll compare it with not used. If it's not used, only then we'll set it to open, and otherwise we'll send -e busy, right, which is a standard error code. So let's see how we can do this. So first I will define this variable, this atomic already open variable, and I will call it static atomic already open equal to atomic init for initializing. So I need to initialize it with a seed value, right? The present state of the atomic variable. For that, I will create a enum for, and I'll call it cdev not used. There will be one value. The other value will be cdev exclusive open. And now we have this thing called already open. The value we will pass is cdev not used. So now we have got our atomic variable and its value enum set up, and now we will use it. So let's define our device open function now. It takes an inode pointer, and it takes a file pointer. So here we'll do our case. We'll try to update it. If atomic cmp xchg already open. So I'm checking for the value of already open. cdef not used. If it's cdef not used, try to set it to cdef exclusive open. And if for some reason atomic compare and exchange fails, atomic cmp xchg fails, we'll simply return -e busy. Otherwise we will simply return 0. Okay, so the next thing that we need to do is define our device release function. Again, the same format. It takes, the two params are same. It takes the pointer to inode, basically an inode pointer, and a file pointer. And this one is pretty easy. All we need to do is atomic set already open, and of course the value should be not used. So no case is happening. We are simply setting it to cdef not used, and we return 0. Okay, so a little bit on this file pointer, and this is pretty important and interesting as well. So this file pointer is not at all same as what you get back from fopen, right? That's more of like a user space file buffered pointer. Like anyways, the fopen allows you to, it's basically a user space functions, libc function that allows you to write and read stream to file, and it returns you a file pointer. But that file pointer, it should not be confused with this file pointer, which is the kernel's structure, kernel's own data structure for representing an open file, right? So whenever you are opening a file, whenever a file description is being created on top of which a file descriptor, onto which a file descriptor points. So whenever a file description is created, so in the kernel, actually a file structure is allocated. A file structure is allocated with various data about the file, and this is how the kernel represents an open file using this file star data structure, right? This file pointer should never be confused with the user space file pointer. Now starts the other interesting parts. So let's focus on the handler for writing a number to the device driver file, right? So whenever we will be writing a number to the device file, it will be added to the existing, like the existing state of the counter. Basically, it will increment the counter, and if required, it will rotate. So let's see how we can do that. So the simple method that we'll be following is we'll have a variable for the counter. Soon I'll be creating a variable called counter, which will be holding the current value of the counter. So whenever we are writing a number to the device file, so what we will do is that we will convert whatever we are getting from the user, we will convert it into a number, and then we will simply add it to the counter, and that's it. And the counter will keep increasing whenever users will write to the device file, and whenever it crosses 999, I believe I said 999. Yeah, whenever it crosses 999, it will loop back to 0, and again it will start from there, right? And reading will be pretty simple. We will get the value of the counter, we'll convert it into a string, and we will show it to the user. Basically, we will send it back as a response to read operation. But here we'll soon be seeing a few pretty interesting things, and that will be like pretty core, and we'll come to know about some of the core concepts in when writing and reading from device files. Okay, so let's get started with that. So I believe the file was, the function name was device, right? And now we'll have to provide the definition for this function. So the first structure is the file pointer, and a common convention is to name it FILP, but again it's just something that people does. Then there comes the user buff, and then size t length, basically the length of the buffer, and we get the offset. Now we can already see a couple of interesting things that's new. The first question is, what's this underscore underscore user? And what is buff? So buff is the variable, rather a pointer to the memory location where the data that the user wants to write to the device file is stored, or rather it's a location at which the kernel module receives the data that it's expected to write into the file, or the data on which it's supposed to operate. So buff is nothing but a pointer to that memory location. It's just a normal buffer. But what does underscore underscore user mean? So remember, two things that I said is that this is the data that's user is sending to us, right? And of course, user doesn't have access to the kernel memory space, right? And the module is working in the kernel memory space or kernel memory address space, right? So the kernel address space and the user address space are completely different, right? So unlike user space programs where you can send from one function, you can send a pointer to another function, and the other function can simply dereference the pointer, right? Either it can, if it's something like an array, it can simply use indexing to access the values, or if you send just a pointer to a integer variable, let's say, you can dereference it using star, right? And or conversely, you can send the address to a pointer using the AND operator or the address of operator. However, in kernel you cannot do that because the address space is not the same, right? It's a completely different address space. So what underscore underscore user signifies is that it's basically a space annotation that signifies is that the buff memory or the content at the buff location is not to be trusted because it's coming from the user space, right? It doesn't belong to the kernel, it's coming from the user space, so it should be accessed in a very safe and secured way. And unlike normal code user space program, which I just said, we cannot directly access the data present at the location buff using indexing or pointer dereferencing. What instead we need to do is make use of the helper functions provided by the kernel, which are known as copy to user, copy from user. Then there are also a couple of other functions which can help us read character by character. But however, we'll be using copy to user and copy from user. And these are like special functions that are provided by the kernel, which knows how to copy data from user space memory location and copy that data to kernel space memory location. So we cannot do normal dereferencing, but we need to access the data in a manner deemed secure by the kernel using these methods provided by the kernel to us. So let's see how we can do that. So first I will define some variables which will kind of model our counter. So our counter, if we think of our counter in string, it shouldn't be more than 4 bytes, right? Its length shouldn't be more than 4 bytes. The last one is for null byte, that is \0. And apart from that, it will have 3 bytes because it will have 3 characters, because it will be a 3-digit number, right? So the string representation will be 3 plus 1, 4 in terms of length. Then I'll have uint 64 underscore t. Yeah, uint 64 is a bit of too much, I know, but if ever I want to play around with a bigger counter, I don't know why would I want to do that, but anyways, if I want to do that, I can use that. You all can anyways use uint 32 or maybe uint 16 as well, right? Okay, so that's our counter and that's our buffer length and counter length. Actually, we don't need this buffer length. Let's just pass the number, only the number that's needed by our counter and not any message with it. That will save us some parsing. So yeah, all that will be able to send to our device driver file is only digits. Okay, so now what I need is I need to define a string. I need to define a string or basically a character array for the string version of the counter. So actually, instead of doing counter length as 4, what I can do is I can make it 3, so that the counter length actually signifies the number of digits in our counter. And while defining the counter string representation, the array, I can do a +1 here, right? Yeah, that way it will be kind of intuitive. Okay, so now we have the counter string, the counter length variable, and now we can start with the function. So I'll define a variable called delta. So delta is nothing but what the user is going to provide to us. I'm simply storing the size of buffer the user is sending to us, and I'll treat it as the counter size, and I'll just do a boundary check here. So if the counter size that I got is greater than equal to counter length, yeah, if it's greater than equal to counter length, then I am going to set counter size to counter length, because remember, all I need to read is the decided number of digits, nothing more than that, right? And now I'm going to use the kernel provided function, which is copy from user, and the first parameter is the destination. When I'm reading it to counter str. From where I'm reading from buff, and how many bytes I'm reading counter size, number of bytes. Okay, if it fails, we just return default. And of course, what would be the last byte of the string? To deem it as a proper string, it will be null byte, that is \0. And another thing I'll update the value of the offset. So remember, whenever you read from a file and you read it in chunks, every time you read it, the offset gets auto incremented to the next position from where you should read. And so we take it for granted when we are using the wrapper function like write. But in reality, it is this offset variable that controls that the value of that offset, right? So basically, this loff underscore t, this type is used to define the offset. And now, since we are implementing the write operation, we need to take care of the offset, which in user space application it's taken care of. In this case, we need to take care of the offset, so that I know in this case we will never perhaps be using the offset, because we won't be reading or writing repeatedly or in chunks. We'll be doing one shot read write. However, it's a good practice to update the offset. And if in future, if you're creating modules where you are writing in chunks or reading in chunks from the device file, you would have to make use of this offset. Okay, I had just missed a semicolon. Guess I've missed some more stuff. Counter length 3, counter length plus 1. Okay, I don't seem to find any other semicolons that I've missed, but I'll let the compiler point out when it compiles. Cool. Next, what I'm going to do is I'm going to use a function called kstr to ull. And what this function will do is basically it will convert the value in the variable delta. And basically what it will do is it's going to convert the string representation of the number present in counter str to a number in base 10, basically a decimal number, and it will store it in the variable delta, whose address we just provided here. Now, only if ret equal to 0, which means the conversion went through fine, what we'll do is we'll just log that we were able to convert or parse. Actually, let's call it parsed number successfully. Once we have done that, we will add delta to num counter. Basically, we increment our counter, and then we'll make a check that if num counter greater than 999, which means time to wrap around or rotate, whatever you call it, number, or rather counter exceeded 999, wrapping over, And wrapping over is pretty easy. It must be greater than 999. So all I need to do is num counter minus 1000, and that shall wrap over. If the counter got increased to 1000, 1000 minus 1000 would set it back to 0. If it's 1001, it will set it to 1, right? Like that. If there is a range problem with the conversion, we would want to log that as well. Value provided is out of range. Else if ret equal to minus EINVAL, that is an invalid number is provided, we will simply log saying that invalid input format, and otherwise a catch all which will say error occurred during conversion, and finally if everything is done, we shall return the counter size. Remember, whenever you use write, the return value of the write system call is always the number of bytes that were written into the file, right? So exactly we need to do that same thing here, and we need to return the number of actual bytes that we processed. So that's why we returned counter size. Okay, so that's our device write function. Now what about reading? Let's do that as well. Let's define device read. Well, once again it receives file pointer, the length of the buffer. In this case, this is the buffer to which we are going to copy the data from the kernel side, right? Because again, in the kernel world, the concept of reading is changing. In this case, you are providing the data to the users. Now we'll do a fun thing. We will basically use sprintf to convert the string version of the counter the numerical version of the counter, that is our num counter, into string version, and we'll simply reuse counter str. Maybe it's not a very good way to do it, but for this simple module it serves this purpose. Okay, my bad, I cannot use length because I'm using len here. Let's call it len c, length counter. Okay, I'll set ret to len c, and if offset is greater than equal to len c or copy to user, again this time we are using copy to user because we are going to copy the content from kernel side to the user memory location or the user provided memory location. And how many bytes do we want to copy? We only want to copy as many bytes as present in counter str. If this fails, or if the offset from which we are supposed to read has gone beyond the length of the buffer provided, then we simply log the same, saying that either reading finished or copy to user failed. Yeah, I'm keeping it a bit dicey. I mean, again, it's a pretty simple function. We do not need to do that much of our verbose logging. And I set read to 0, means nothing, just 0 bytes read. Else I'm going to, same thing again, we need to maintain the offset, right? Just like we did for write. Because again, whenever you are reading from a file and you are reading in chunks, you always know which is the next offset from which you need to read, and you never take care of it, but the read system called the same for write, as I mentioned, that you know where to write next once you have written the previous chunk. And finally we just return read, and that's it. That's our simple kernel module implementing four handlers for us: device read, device write, device open, and device release. Okay, so now that our module implementation is ready, now we'll try to build it. First we'll try to build it on our machine, like on my machine on which I'm developing it, and then we will build it on, we'll sync the source to the Pi 0. There we will try to build an INS modded. So let's first try to build it here. Okay, so now here what I'll do is I'll run make, and it compiled successfully. Interesting. Without any errors, which is good. Okay, so now what I'm going to do is I'm going to SSH into the Pi 0. So now I'm inside Pi 0 in my the bottom terminal, and I believe the directory was cd yt. Yep, this one was the directory inside hello world. Let's keep the name hello world as it was, and I'm just going to sync this just to ICP. So let me do a counterdev.c to 192.168.68.61, and what I'll do is I'll do a pwd, copy this and paste it here. Okay, and now I'm going to divide this one as well, because I want to see the dmessage output. Okay, so on this terminal also I'm inside dmessage, and let me just check the current status of dmessage. Should be empty, mostly empty. I'm just going to tell the last 10 lines. Yeah. Okay, so let's compile, and it's done. Now let's INS mod. Yeah, INS mod counterdev ko. Let's see what came here. Yep, it has been assigned a major number. And now what I'm going to do is, so I know as usual the character device file has been created, so now I'm going to echo a number, let's say 20. I'm going to t it to dev/counterdev, and now I'm going to read from counterdev. Let's see what I get. Sudo cat dev counterdev, and looks like there is a bug. For some reason it's going into a infinite loop and it's continuously printing 20. So one thing we know that it did store the value 20. So our write handler is working, read handler is also working. That it did spit out something to the screen to cat, but there is a bug and we need to debug it. So we are taking the file pointer, then the cat buffer from user space, and the length, which we are calling len, and the offset. Okay, so here is the bug. It should have been length, because length is pretty much the length of the string counter, which contains the string representation of our counter value. And yeah, so length is the length. That's why we are doing a size of over here, and then we are copying lengthy amount of bytes from counter string to buffer, which is pretty much the entire counter string. Okay, so lengthy is pretty much the number of bytes we are transferring to the buffer. And it's good to have a check here whether if lengthy is becoming longer than len, because that's what the number of bytes the user space function wants to read. But I believe our number of bytes is extremely small and it should suffice. If it doesn't suffice, we shall soon know if there is a problem. But yeah, for now I won't put that check, and if there is a problem we'll try to fix it. But for now I just keep it that way, and here I'll just do a lengthy. I'll update offset by lengthy, so next time when it tries to read, so the thing with device read is, as long as the offset or the return value is, as long as it's not zero, the read system call will keep on trying to read from the file, because it will think that there is still content to be read from the file. As long as it is non-zero, it will continue to read. The moment it becomes zero, it will exit. We are increasing the offset as and when we are reading. In this case, we are increasing the offset at once by length, because that's the length of our counter, by which I mean number of characters or number of bytes. So in the first go itself, offset will get increased by length c, and this condition will get fulfilled. And in the second iteration itself, like the first iteration is for actually doing the copy to user, in the second iteration itself, red will become zero and the read operation will be over, right? So I believe this should fix it. Again, first thing I'll do is I'll rm mod it. I believe it's still there. I did not remove it. Okay, I just rm modded it. We must have received this thing. Yeah, device driver unregistered. So it could actually parse the number successfully as well in the last attempt. So I'll just try to ins mod it once again. Okay, if I do this, it got registered, and now I'll do the same thing again. I'll try to do a echo t, and it said parse number successfully. And now I'm going to do a cat. Nope, it's still not fixed. This is interesting. If I again do a 20, should it return a loop of 40? Yes. So our addition logic is also working. It's just that the loop is not ending. And why is it not ending? That's what we need to figure out. There's our buffer. Oh, damn. Yeah, I was increasing the pointer, but not the value at the pointer. That was silly. Okay. We know the drill. Compile. Okay. Once again, I'll do a ins mod. Now this time, once again, I'm going to do a echo 20, and yeah, parse successfully. Now I'm going to cat it, and it worked, right? This we were aware of, that we didn't want to put any \n, right? So that it can be parsed programmatically without much of an hassle. We just wanted to output the number, nothing else, no special characters at the end. So now let's add something, right? Let's add 100. What happens? It becomes 120. Let's add 120. It becomes 240. Now let's add 1000 to it. So what should we get? It should become 1000 and 240, but then wrap back to 240, right? Okay, so there seems to be some issue. Whenever it's crossing 1000, somehow magically extra 100 is getting added. What did I do over here? I'm subtracting 1000 from the final value, but that doesn't seem to work. Let's debug this further. Why is it not behaving the way that I want it to behave? So what's happening is, okay, so it's 540. If I add 459 to it, what happens? 459. So it's 9 and 9. If I now add 1, does it function the way we want? That worked as expected. Now if I add 1000 to it, what happens? And it becomes 100. That doesn't seem right. Okay, So the problem that's happening is I cannot add, if I keep it 3, the delta that the input that I'm giving to device file via echo, that cannot be more than 3 digits, right? So for the purpose of this video and for the purpose of this toy counter that I'm building, let's consider that the delta can, or whatever the input that I'm giving to the file, that can be of 4 digit. I can add, if I want, I can add something like 1000 to the file. It will rotate beyond 999. That's a different thing. But at least I should have the ability to add a 4 digit number to the counter and let the counter wrap. Ideally what we should do is like increase in real world, increase it further. Like we can choose a proper boundary, like 6 digit, 7 digit, depends on how big our counter can go, whether we want to support a million or 10 million, 100 million, whatever, because we already have u64. But yeah, again, as I mentioned in the starting of the video, I'll just stick to 3 digit numbers. For the counter, I will just stick to 3 digit, that is 999, and for input I will allow 4 digit, but I will make it wrap after or rotate after 999. And I was just thinking, like, there are some other very basic flaws here. Let me just fix those quickly. So when I'm reading into counter str, that is, I'm converting num counter to LLD and storing it in counter str. Before doing that, I should kind of always do a memset. Now you might ask me that, hey, memset is a user space function, right? Where do I get memset from? So in user space, we would usually include string.h, right? But in kernel space, or in for kernel module, what I can do is I can simply include Linux string.h. So the kernel does provide us with an implementation of string.h header, basically the string.h provided functions, right? And good for us, memset is one of the functions for which the kernel provides us an implementation. So let's do that. So it's a good practice to, before tampering with counter str, we'll just make it all 0, right? We'll just make it a null string. Okay, so this is the one. What I'm going to do is, it is a normal memset interface. The first thing that it takes will be the buffer, which is counter str, comma 0, comma counter length, and of course +1, right? Because the counter length is just the number of digits +1 for the null terminator. So the entire array, entire buffer would be initialized with null bytes or set to null bytes. Okay, so this is one thing that I wanted to do, and same thing I would repeat the other place where I'm using it. Yeah, just here before I do copy from user. And the other basic mistake I have made here is where did it go? Is this one. This in reality doesn't make any sense. Like, this shouldn't have been minus. What it should have been is modulus, right? I believe this is pretty self-explanatory, and the mistake I did was really a sad one. So yeah, now I believe everything should work fine. Okay, so the last thing that I want to check is that we are able to lock the file, right? By lock, what I mean is that, remember I said that at any given point of time, only one instance to this device driver file can be opened, right? So let's see if that part is working, for the reason for which we implemented the cache and the lock. So let's see if that works. What I'm going to do is that to test that, I'm quickly going to use Python. Let me add some more, just like that, some more values to the counter. And let's see now what's the value. It's 280. But anyways, we won't be needing to know the value of the counter. So for that, I'm going to use Python for just quickly testing this locking thing. And here, so see how I used sudo so that it can access the device file, because right now the device file is only accessible by the owner, which is root. And so what I'm going to do is I'm going to open an instance of the device driver file, and that's counter dev. That's it, and do nothing. So now if I try to cat the file from another terminal, so basically from another process in this case, and we got device or resource busy, which was expected. Why? Because of the cache. It knows that one instance of the file is open, right? Which it stored in that atomic variable. Just let me show you quick. We use this atomic underscore t already open variable, which can get only these two value, and on this we are doing a compare and swap. So since it's already open, it didn't allow the cat process to open it again, right? Even if I try to do this once again inside Python, in this inside the same process, it won't, because already one description is open for the first call of open, right? So that's why it won't allow me to open the. Now the moment I close it, let's see, now it can read. So the lock was released by the Python process, and it could be used by the cat process, and it could read it. So as simple as that. So yeah, there we have it, our tiny device driver, a character device driver, a kernel module, which acts as a pseudo counter. And using that, we can just write numbers to the device file, and those numbers will get added to the counter. The counter will keep that value for us, and it will allow us to count till 999, and after that it will simply rotate. And all this in just how much? Roughly 160, if I just get rid of some blank lines. 158 lines of code, right? So yeah, that's what I wanted to do in this video. I wanted to play around with kernel modules, especially character device driver. So there are lots to do with Linux kernel modules. You can even create your own proc file. You can create your own entry in procfs, that is /proc, with which again the /proc file will act as an interface for you to interact with the kernel. You can create block device driver files and so many things, right? Which we'll find out in the other videos. But for this video, I just wanted to create this character device file, play with this counter, and just walk you all through a simple character device driver, or basically a simple kernel module, Linux kernel module. So yeah, I hope you all like this video. Let me know if you have ever written a kernel module from scratch, even whether it be it in your academics, in your university, or in your job. Let me know what module you have written, what it does, if it's open source, if I can see the code. Do let me know in the comment section below. And yeah, thanks for watching, and see you all next time.